All right, good afternoon, everyone. We'll go ahead and get started today. We'll be talking about vehicle efficiency. Okay, so kicking things kind of right off. This is kind of a caveat right at the beginning. This is what we're talking about is efficiency is actually efficacy. If you've taken physics, right, we know that energy efficiency is technically a dimensionless number, and it's always between 0 and 1, right? And so you always have numerator at the same units as your denominator. So efficiency is often used to refer to ratio of output and input, even if they don't have the same units. And so, for example, right, we've talked a lot about like gasoline fuel efficiency, which is in miles per gallon, or an electric vehicle efficiency in kilowatt hours per mile or miles per kilowatt hour. So technically speaking, efficacy is the correct term to use here, but we're just going to kind of substitute in, I'll be calling it efficiency. So efficacy is defined as like a service output compared to an energy input, right? And so miles per gallon, the miles is your output, the input is the gallons. Maybe just for fun, right? Miles is a unit of length, and gallons is a unit of volume. So if you had a miles per gallon number, let's say like 25 miles per gallon, does anyone actually know if you like divided out the length, right? So which is, let's say in miles, and then you had volume in terms of gallons. If you cancel that out, does anyone know what that would actually represent? Any ideas? So if you had a unit of length over a unit of volume, you would end up with a unit of area on the bottom. It actually is, if you had 25 miles per gallon, that would be the cross-sectional area of the gasoline that if you stretched it out over 25 miles. In reality, the efficiency numbers that we kind of use don't really physically, mean anything in the terms of the actual efficiencies that we think about in physics, but they're useful metrics for us to know. And so for gasoline fuel efficiency, right, so this describes the distance a car can drive given some amount of fuel, and that allows us to directly compare between different types of vehicles. So I think I talked about this kind of on the first day, right? In the United States, we measure fuel efficiency in MPG. Hopefully everyone's relatively familiar with this number, right? And that indicates how many miles I can drive on a gallon of gasoline. But most other countries in the world measure things differently, right? So they actually not only use different units, right? So liters instead of gallons and kilometers instead of miles, but they also flip that efficiency number as a consumption number. So it's liters per 100 kilometers, right? Which would be the equivalent of having your gallons on top and your miles on bottom. Right, and so this is an indicator of number of liters of gasoline it takes to drive 100 kilometers. So technically there's equivalence between these two things, but there's kind of an important principle here to think about. And so I'm going to do a little example right now. So, all right, hang on, we'll jump over here. All right. Okay, so let's suppose we had two cars. We have car A and we have car B. So car A is a 20 mpg vehicle and car B is a 40 mpg vehicle. And what I want to do is I'm going to upgrade these cars. So car A, I'm going to upgrade from 20 mpg up to 25 mpg. So this is a plus 5 mile per gallon improvement. For car B, we're going to go from 40 mpg up to 50 mpg. So this is a plus 10 mpg. Okay, so my question to you guys is, we have these two vehicles, and I'm gonna upgrade. I get to choose to upgrade one of these. So raise your hand if we think adding 5 mpg will result in more fuel savings compared to adding 10 mpg. So raise your hand for upgrading car A. Okay, and now raise your hand if you think upgrading car B will give you more fuel savings if we did plus 10. Okay, okay, a bunch of people raised their hand for the second one. Didn't see many for the first one. Okay, so if I were to drive 100 miles, then the amount of fuel savings I would get is 100 miles divided by 20 mpg minus, oh, actually I should do it the other way around. 25 mpg minus 100 divided by 20 mpg. Okay, and so 100 divided by 25 is 4. And, oh no, I did it right the first time. Okay. So 100 divided by 20 is 5 gallons. Minus 100 divided by 25 is 4 gallons. So by making this upgrade, I save 1 gallon. Whereas, if I drive 100 miles with car B, we would have 100 miles divided by 40 mpg minus 100 miles divided by 50 mpg. And so 100 divided by 40, that's 2.5, minus 100 divided by 50, that's 2 gallons. And so this only saves half the amount of gasoline compared to doing car A. So this first switch is actually better, right? Even though it looks like you're only improving half as much as car B. And that's because when we're looking at the consumption of fuel, right, you're actually looking at the inverse ratio. And so the whole idea is MPG is actually a very poor metric for kind of describing the relative amounts of consumption over set distances. It's actually a 1 over X. And the main takeaway here is that actually improving the fuel efficiency of like really, inefficient, dirty, big vehicles is actually going to be a lot more efficient or save a lot more fuel and energy than upgrading vehicles that are already pretty fuel efficient, right? And so if I had the choice to upgrade between an old truck and get it a little bit better compared to, if I already have a pretty efficient like hybrid and then getting that to be even more fuel efficient, the first one is going to give a much better efficiency benefit. Okay? Any questions? Yeah.
When you're talking about the actual usage, it's what? It's using 5 gallons.
Right, but we're talking,
100 miles.
yeah, but we're talking about, like, if you were budget constrained and you got to choose to improve one of these two vehicles, right, which one would make more sense to improve? It's not, right,
From point A to B though, you would spend more money.
well, we don't know that.
You got 5 down.
So, okay, I wanna kinda clear up the, confusion here. It's not saying that car B is worse than car A, right? It's definitely more efficient, right? It saves more, it is more efficient at the outset. I guess the bigger motivation is thinking about if I had to direct resources to improve the fuel efficiency of the fleet of cars, right? Which is, something that's already on the road, right? It's not choosing between A and B. It's choosing which of A and B would actually improve more in terms of fuel savings. So car A certainly consumes more fuel. But it's actually worth more to slightly improve car A than to improve car B. Any other questions or comments? Sorry, what was it? Oh, yes.
Why is the inclusion measure in per distance rather than per driving hours or something like that? Why do you measure per distance?
So ultimately, the service that we care about that the car provides is getting you from like point A to point B. And so the usage is all tied to distances. Yeah. Okay, any other questions? So actually, I will mention that the reason for this sort of phenomenon happening is because we use MPG. Most of the other world, by inverting it, it actually linearizes all of the gains. And so if we were to compare, for example, and I were just to take 1 over each of these, this would be, this would end up looking something like a 1 over 20 or 0.5 going to 1 over 25, which is 0.4. So this is gallons per mile, whereas here, 1 over 40, right, this would be 0.25 going to gallons per mile, going to 0.2 gallons per mile, right? And here, you can actually see the difference, right? So this is minus 0.1 GPM. So it's also inverse, right? So the less gallons per mile you consume, the more efficient, whereas here it's only minus 0.05 gallons per mile. So if we were to use the inverse metric of miles per gallon, then actually you could do this in a much straightforward way and you didn't have to make all of these sort of calculations. So yeah, miles per gallon, not my preferred metric of sort of measuring efficiency. And there's a whole actual, someone actually published a paper about this, many years ago in Science. So MPG scales nonlinearly with fuel consumption, and it makes calculating fuel savings extremely counterintuitive. That's actually one of the reasons why. So has anyone ever seen an infographic like this before? No one's bought a car in the recent past? Okay, so if you were to go to a dealership, you would see this little pamphlet kind of stuck up against the car windows. It's actually a requirement for new cars to display this information. They have one kind of equivalent for gas cars. This one I'm showing is actually for a plug-in hybrid, so you can kind of see on both. And what they show you is the fuel efficiency measured in miles per gallon on the gasoline side. And then there's actually an electric efficiency that they term MPGE. So that stands for miles per gallon equivalents. And we'll talk in a lot more detail about how that number is calculated in a second. And because of the counterintuitive nature of being able to calculate those fuel consumption metrics, they kind of do that for you, and they give you this estimate of how much it would cost on average for you to pay for fuel over the course of a year, so that consumers don't actually have to do the math to kind of understand what those consumption numbers actually look like. And then they have these metrics where they compare it against the average vehicle. And so for some cars, right, you'll save money compared to the average car. For others, you may be lower, or you may actually lose money. You would have to spend more on average than most other cars. And then they actually have some information about its relative fuel economy and its emissions, as well as its smog rating. So this is essentially this little infographic that the US EPA and Department of Transportation kind of coordinated and worked together to generate. You can also find all of this information for all cars online at fueleconomy.gov. Yeah, and so that actually will give a little bit more information than what's shown here. But when you go to buy a new car, yeah, you can expect to see this type of information displayed on all new cars. Okay, any questions about this? All right. So MPGE, what is that? So miles per gallon, MPGE stands for miles per gallon equivalent, as I was just mentioning. And this is a really sort of artificial metric that was devised as a way to kind of compare gas cars to electric cars. But remember, EVs don't consume any gas at all. So where the heck does this number come from? So they convert electricity use from electric vehicles into gasoline based on the energy content of the fuel. So we know that 1 gallon of gasoline contains about 33.7 kilowatt hours of electricity. And that number comes from the actual energy content of gasoline. So you can convert it into BTUs, and then there's a conversion between BTUs and kilowatt hours, right? It's all just in terms of joules. And then you can calculate into different units or metrics that you want. So, yes, yeah.
How do you get the efficiency though? Since again, cars are typically less efficient than a car plant using the same fuel.
Yeah, okay, great question. And that gets to some of the controversy behind MPGE. So this energy quantity, 33.7, is the actual total amount of energy contained in gasoline, right? You don't actually get that into equivalent amounts of energy when you combust gasoline, right? Because you lose a bunch of efficiency. And similarly, for electricity, you're going to lose some of that as well. And so I'm going to talk about where that comes from. This particular number just assumes that there's no losses. So it's going to overinflate what the actual MPGE is when we think about how efficiency plays a role, right? Because it basically assumes that the gasoline is fully converted into electricity, essentially. So let me get back to that, because we're going to talk about that in more detail in a second. Yeah, so here are a bunch of examples of vehicles in the last like 15 years, and we can see what those efficiencies look like. Um, so they're not, uh, they haven't been calculated out in terms of the full ratio where you can look at the actual kilowatt hour per individual mile. This gives us the battery capacity and um, the, the mileage range of each of these vehicles. So you could do that division and then figure out what the kilowatt hours per mile would be, or right, the way that we do in the US, the miles per kilowatt hour. And you can see there's generally a pretty broad range of both battery sizes and ranges. If you were to actually divide them out, you would also see a pretty large range in efficiencies as well. So when we think about, so I'll use a number, so kilowatt hours per 100 miles. Generally, you're going to find something on the order of like 25 kilowatt hours per mile for very efficient electric vehicle, all the way up to like 40, 45 kilowatt hours per 100 miles for a very inefficient electric vehicle. So that might be more like a, like a Giant's like Hummer EV, for example. I think that one is even worse. But like a Cybertruck or F-150, those are going to be like 40 to 45 kilowatt hours per mile, whereas something like a Ionic 6 or like Lucid, I think are going to be closer to the 0.2 to 0.25 kilowatt hour, 20 to 25 kilowatt hours per 100 miles. Okay. Okay, so going back to this idea of where that MPGE comes from, part of having the MPGE is this like kind of comparison for consumers. Again, I kind of question how useful that is, but it's also fundamentally important for complying with some of the regulations that require you to meet some kind of fuel efficiency standard, right? And so for a long period of time, let's say an automaker has to meet a particular target of like MPG for all the vehicles that they sell. That is more straightforward when you have just gas cars. But then once we're introducing EVs to the mix, how do you kind of mix those together, right? And so the MPGE is a way of doing that. So there's we're going to talk about this later on in this course, but there's essentially two regulations when it comes to efficiency. One is by the EPA, and they are responsible for measuring emissions coming out of all vehicles, and that number is actually directly equivalent to MPGs. There's a specific conversion factor to go between miles per gallon, and the metric for emissions is grams of CO2 per mile. So the EPA, it's less relevant because they count electric vehicles as just having no emissions. And so that part we'll talk a little bit more about emissions related to EVs and environmental consequences a little bit later. But in the meantime, as we're talking about efficiency, so the US DOT, one of the groups under the US DOT is the National Highway Traffic Safety Administration, or NHTSA. They're the ones responsible for fuel efficiency regulations, and they use what's known as a petroleum equivalency factor to convert EV efficiency to petroleum efficiency. So remember how I was saying that originally the calculation is this like 33.7 kilowatt hours per gallon of gasoline. More recently, they took an updated approach in order to actually think about the efficiency of energy conservation when we start from primary energy. So primary energy, for those who don't know is the form of energy that we would, in its kind of rawest form, that we're extracting from nature. So, yeah, the old approach used this 80,049 watt hours per gallon. And the new approach in the regulations is to use this updated one, which includes kind of an averaged out efficiency loss of primary energy to electricity. So that's kind of the answer to that question in terms of, you know, how that number actually is converted. So just to give people a sense of what that looked like, so in the old way that we did things, the CAFE MPGE, the CAFE being the fuel efficiency regulations, right? So for like a Volkswagen ID4, it used to be 380 miles per gallon equivalents, and now it's 107. Ford F-150 Lightning used to be 237 MPGE, and now it's 67.1 MPGE, right? And so the miles per gallon equivalents were really deflated a lot once you actually try to account for efficiency losses in that conversion. And again, all of this is like very artificial, right? Because miles per gallon, it just isn't, it doesn't really make sense to do that for electric vehicles, right? Because they don't consume gasoline. But for the sort of broad consumer and for the purposes of like these regulations, right, we need some way of equating them to gas cars. MPGE is probably going to stick around for a little while. I would guess that, you know, once the broader market is, you know, really comfortable with electric vehicles, that we probably might move away from this. But until then, yeah, this is probably the metric that's going to be around for a while. Yeah, so MPGE versus miles per kilowatt hour, they're kind of the same in concept. And from a relative portion, when you're doing relative comparisons between MPGEs, I guess that kind of makes sense. Yeah. Any questions about this? Okay, so maybe a quick discussion. Do you guys think MPGE is a useful metric, or does it create more confusion than clarity? Should we just kind of stick to one metric, or should we still have this? I'll let you guys discuss for a minute or two, and then we'll reconvene.
It just depends on which metric you want to for like miles per gallon versus the issues is like even if these are I think it's more like who is the stakeholder, which one is useful for. So I think for like an everyday consumer, you know, like researchers,
Okay, let's reconvene. I forgot my ball at home today, but okay. How about you guys? Well, what did you guys talk about?
I kind of mentioned that, like, well, it depends. I think, like, for, like, a consumer level, like, not really. But, like, probably for, like, industry or, like, research purposes, I think it's more useful. So I think, like, it just depends on, like, who the stakeholder is. It depends on how useful the metric is.
Okay.
So, like, if you're looking at, like, everyday consumer now, that's not going to apply.
Okay. Anyone else? You guys want to volunteer anything?
Yeah. I think miles per gallon equivalent is, yeah, does just create more confusion. So that, I guess from a consumer standpoint or from a marketing standpoint, it's kind of nice to show big numbers to get people's attention,
Mm-hmm.
but it does kind of conceal information about the methods used
Yeah.
to calculate it, like what assumptions are being made,
Yeah.
conversions.
Yeah, great. So actually, let me do a quick informal survey of the class. If you guys were going out to buy a car, how many of you guys would prefer to see an MPGE, or would you prefer to see like a miles per kilowatt hour? So raise your hand for MPGE. Okay, and then raise your hand for miles per kilowatt hour. Okay, yeah, great. So yeah, maybe we can assume that it's a little bit split. We see on both sides, but that maybe we should trust consumers to be able to understand, right, a new metric. Yeah, I don't know what the right answer is, but they're both going to be around for a while. So. Maybe, although I would be more wary that the familiarity comes from electricity. I don't. I also do a lot of work in the power sector, and I think consumers in general, I would say, there's less understanding of what's on the electricity. Like, who knows their electricity bill pretty well when it comes to that? So you're raising your hand, but not so many other folks in the room. So yeah, I wouldn't necessarily count on that. Okay, so yeah, let's dive a little bit more into detail about the comparative efficiencies between gas and EVs. So I think we've covered this a little bit, but let me go into a little bit more detail here. So I'm sure that folks have probably heard that electric vehicles in general are more efficient than gasoline, and I would say that's kind of true. And it depends on the way in which we're kind of looking at the ecosystem of efficiency. So this diagram right here is just like a really simplified diagram of a gas car. So we've talked about this. From our combustion engine, right, about 65 to 80% of the energy in gasoline is lost to heat in combustion and friction. And then, the rest of that energy is going to go into moving the actual vehicle. That range, it's a lot narrower when we just think about engine translating to wheel, translating the gasoline engine, gasoline fuel into movement in the wheels. Most of that range is kind of probably going to be more like 20 to 25%. The rest of that gains is only really for if you're recovering some of the energy from like regenerative braking. And so that 35% is really going to be the case for hybrid vehicles, right? And so when we think about the translation in efficiency on the consumption end of things, this is something like 0.03 to 0.04 gallons needed to drive a mile. So on the other, for the other technology, right, for electric vehicles, looks something like this. We have about 60 to 75% of energy in the battery translated to work to move the vehicle, and 25 to 40% of the energy from the battery is lost in kind of friction. But all BEVs are going to have regenerative braking, and so your efficiency ends up much higher. You're going to be kind of on the 80 up to like 95+%. This is 100%, but that's, you can't actually get 100%. Yeah, and so when we think about kind of the efficiency and just the drivetrain piece of it, it's going to be quite a bit more efficient. So this is on the order of like 0.35 kilowatt hours per mile on average. Whereas if I were to think about that in the same units for gasoline, that would be more like on the order of 1 kilowatt hour per mile. However, we will also have efficiencies from the production of electricity, right? And so depending on the source of the electricity, you are reducing the life cycle efficiency of your electric vehicle technology. It's still going to end up being higher, right? Because if we're saying like a natural gas combined cycle power plant, let's say that's about 60% efficient, and our electric vehicle we'll say is like 90%, right? 60% of 90%, that's still going to be 50 to 60% in total efficiency. So you're still quite a bit more efficient than your gas car, right? But that difference is shrunken by quite a bit. Okay, and you also have some minor losses in like transmitting the electricity, through your transmission and distribution system. That might be like anywhere between 3 to 5%. You may have some efficiency losses in converting between AC and DC, right? We've talked about that. But altogether, it's still going to be more efficient than a gas car. So at a high level, if you're thinking about just the cars, right, then the gas car efficiency, you're only getting like 25% out of the fuel, whereas with an electric vehicle, you're more on the order of like 85 to 95% out of the electricity. And then when you include all of the life cycle stuff, if you're including the upstream efficiency decreases, then you're more on the order of like 40 to 60% for electric vehicles, depending on the source of the electricity. Okay? Any questions about that? Okay. I already kind of mentioned this. This is kind of the range of efficiencies. This is in kilowatt hours per mile. Right, so as I was saying, the Hummer electric is about 0.8 kilowatt hours per mile. That's kind of the least efficient, whereas your most efficient vehicles down here are going to be closer to like the 0.2, 0.25 kilowatt hours per mile. And most are going to be in the range of between like 0.3 to 0.4 kilowatt hours per mile in terms of efficiencies. I'm kind of interchanging between a bunch of different efficiencies for EVs because actually there isn't, I would say, a well-recognized standard for this yet. And so I may jump between miles per kilowatt hour, kilowatt hours per mile, and then kilowatt hours per 100 miles. You will likely see efficiencies for EVs kind of displayed in any one of these three metrics pretty commonly. And then, you'll be able to, at some point, if you're getting a lot more familiar with this, you'll be able to do that math pretty quickly. Okay, for plug-in hybrids, we have anywhere between 1 kilowatt hour per mile, which is very inefficient, all the way down to about 0.25 kilowatt hours per mile, which is kind of the high-end efficiency as we've seen compared to the full battery electric vehicles as well. Okay, and so there's an even bigger range in plug-in hybrids. Their motor efficiencies and converter efficiencies are not always going to be kind of as robust as with battery electric vehicles, and that's why we see some of the efficiencies being up quite inefficient at that high end in comparison to BEVs. Okay, so I'm talking about all these efficiency numbers, right, from all this big range of different electric vehicles and plug-in hybrids, and even for gas cars, right? You go to a dealership, you see this one number for MPG. You might actually see two numbers where they have like a city MPG and a highway MPG. Okay, and so does anyone know where these efficiency numbers actually come from? Any ideas? Okay, so efficiencies are actually calculated in a standardized way. So this is a picture of a dynamometer. These are essentially these measurement tools that you can use for your vehicle. You can think of this almost like a treadmill for a car, right? And so it will sit on top of the dynamometer, and you could just drive the vehicle, and it actually has these kind of rolling pins so that the vehicle is staying in place, and it's just rotating those, and you can make a bunch of measurements on a whole number of different diagnostics for a vehicle. And so regulatory agencies like the EPA, they use these to do things like measuring emissions under these sort of standardized testing cycles, which we're going to talk about a lot more in just a second. Okay, so I mentioned just now that it's the EPA that's doing these measurements, and they're doing it for emission purposes, but actually a lot of these tests that are done for vehicles are able to measure multiple things that different stakeholders would be interested in. And then, as I mentioned before, if you're measuring the CO2, you could actually elicit the fuel efficiency or kind of vice versa. And that's actually a good way to validate that you're getting the right values for these things. So there is a direct relationship between emissions and vehicle efficiency, as I was mentioning before. So if you have a car and you put in some amount of gasoline into it, you will be able to understand, how much distance that vehicle can travel given a set amount of fuel input, right? And we measure that as MPG. You also will know how much emissions are coming from combusting that gasoline, right? So assuming kind of perfect combustion, 1 gallon of gasoline will always result in the same amount of carbon dioxide, right? Regardless of how far that vehicle is moving, the actual chemical output of the combustion process is just CO2. It's the oxidized fuel input. So even as the fuel efficiency of the vehicle changes, the relationship between your MPG and emissions per mile will always stay constant, right? And so if I wanted to go between those two, the metric is this conversion number here, which is 8,887 grams of CO2 per mile. And so I can go between grams of CO2 per mile and MPG using this particular metric. It's not something you have to memorize. If I ever ask you to do conversions, I'll provide that number to you, right? But this is the number that the EPA uses to convert between emissions rates and fuel efficiency. Okay. Going back to thinking about the calculation of efficiencies, right? There's kind of an interesting thing to think about, which is that when you guys drive your cars, whether they be gas cars or electric vehicles, have you ever noticed that if I'm driving, let's say, in the city versus if I'm driving on the highway, my fuel efficiency is actually different, right? The amount of fuel that I consume actually depends on the condition, my sort of driving conditions. So a vehicle efficiency can vary at different vehicle speeds. And so I mentioned this before, right? But that has actually to do with the operation of the actual drivetrain. For an engine, there's actually an optimal speed in which I can get kind of the most bang for the buck out of my gasoline. And similarly, for electric vehicles, your motor can operate most efficiently at certain ranges of speeds as well. So for gas cars, engines tend to operate most efficiently at around like 45 to 60 miles per hour. Whereas for electric vehicles, most of them tend to operate at peak efficiency from like 25 to 30 miles per hour. So there's actually a pretty big difference there. And so if we think about this idea that like when I go to a dealership and I want to look at a car, or you're doing research on like a car that you want to buy and you're trying to understand efficiencies and you get this one number, well, like where does that come from? Like why is there just one number if like I drive on a highway and then it changes a lot compared to if I'm driving in the city, right? And so how do they make a choice about where that number comes from and how that relates to how much like highway driving versus city driving versus how much you're blasting your AC and all of these things, right? So even if two people were to drive the exact same distance, right? If one person is, if you're driving to Davis, from Sacramento, two people could be going in the same car, the same distance, but actually have pretty different fuel efficiencies. And that is related to the way that you're driving your car. So in order for, agencies to have a fuel efficiency number that they can show, they actually have to come up with standardized procedures in order to have that kind of one fuel efficiency number. So I'm going to talk a little bit about the different standardized test cycles that are used around the world that are then used to essentially calculate fuel efficiencies for different vehicles. Okay, so the first one that I'll talk about is the NEDC. We're gonna do the international ones first. So this is the new European driving cycle. And this was meant to represent kind of typical car usage in Europe. And what I would say about the realism of the numbers coming out of this particular, what we call this test cycle or driving cycle, is that they tend to overinflate efficiencies compared to what you would see in reality. So the dynamometer, the rollers, they are meant to emulate a lot of the resistances that you can get from aerodynamic drag and from vehicle mass. And here, there are, what you're looking at here, the plot on the right-hand side, this is known as a speed trace plot, okay? And so over time, you have a car accelerating and then going at a certain speed and then decelerating, coming to a stop, accelerating again, going up to a higher speed, maintaining that speed for some amount of time, and then slowing down, and so on and so forth. We can see that the speeds that are being reached here are like 20 to 40 kilometers an hour, which is, yeah, like relatively so. I mean, this would be indicative of something like city driving as opposed to highway driving, right? As opposed to in the latter half of the speed traces, you're having a little bit more like higher speed driving, and that would be more indicative of like driving on a freeway, for example. These particular speed traces were designed to emulate the conditions of driving around in like a European city. And so they have these 4 urban driving cycles. This is known as, these individual little speed traces here are the standardized UDC/ECE. That's the kind of name for these parts of the cycle. And they are low load, low exhaust gas temperatures, max speed of 50 kilometers per hour. And then at the end, you have this extra urban driving cycle that's more aggressive. And so again, just to reiterate, NEDC, this is an outdated test cycle, no longer being used. And one of the biggest flaws is how different the numbers being generated, the efficiency numbers coming out of this test cycle were compared to what people were getting in reality, right? And so, if you were to drive like a Toyota Camry or something like that, and you were on average getting like 35 to 40 mpg, this might be telling you that, oh, Toyota Camry, when we do it on this test cycle, you might actually get like 65 to 70 mpg, right? So it would really heavily overstate the efficiency. So nowadays, there was a newer standard that was developed called the Worldwide Harmonized Light Vehicles Test Procedure. This is a set of test cycles that were standardized to essentially replace the NEDC. And the idea was to sort of better match those lab estimates and emissions with what we're actually seeing on road. So WTLP, I would say, still overestimates your fuel efficiency, but not nearly to the same extent that NEDC was. The other thing about WTLP is that it's harmonized across the world, and so the test procedures maybe depart a little bit more from the original NEDC, which was meant to emulate a lot of the city driving. The speed traces go on for a much longer period of time and are a little bit more dynamic than what you were seeing in NEDC. These particular examples are across different classes of vehicles, so this would be more on the like passenger vehicles, whereas class 2, class 3, you're getting to like heavier vehicle classes, right? And so here they're kind of differentiating classes with the different test cycles. Okay, any questions about this? So again, these still aren't perfect representations of efficiency. They are very consistently biased upwards, but compared to NEDC, they are a big improvement. So NEDC and WTLP are the ones that are used pretty standardized internationally. In the US, we actually have a different set of test cycles that are maintained by the EPA. So prior to 2007, EPA would use a city cycle and a highway test cycle in order to calculate fuel economies. There's a standardized breakdown. So when you get a single fuel efficiency number, it's combining the two cycles, and they assume that you drive 45% on the city cycle and 55% on the highway cycle. And they still use that kind of ratio today, but a lot of times you might actually see them broken out into highway and city, so that consumers have kind of a better idea based on how much they understand they would be driving on those two, in those two conditions themselves, right? Because some people tend to drive a lot more on highways, some people will drive more in cities, and so getting both numbers lets you kind of do that calculation customized to your usage. Two-cycle test, kind of like the NEDC, not a great representation and typically would overinflate your efficiency numbers. Starting in 2008, EPA added 3 additional tests, and that combination of tests is known as the 5-cycle test. And so really you can think of like the 2-cycle test as analogous to the NEDC, and the 5-cycle test is kind of analogous to WTLP. The 5-cycle test is a lot closer to reality, but I would say still overinflates fuel efficiency on average. So the speed traces of these test procedures looks something like this. So you have city, it's formerly known as UDDS, highway is formerly known as HWFET, but the speed traces look something like this, right? And so this is really kind of what you would expect to see in a city, right? You're driving around and you have a lot of start and stop, right? So accelerating and then decelerating, you know, as you go, and you're like hitting stop signs or stop lights at different intersections. So your city test looks like this, whereas the highway test, you're never really coming to a stop, right? You are at some speeds, you might be slowing down and speeding up in some places, but in general, yeah, you're going to be operating in your speed trace at higher speeds. The 3 additional tests that were added are these 3 here, and they add extra conditions that make you do things like the engine might be operating slightly differently at cold temperatures. You might be using like a heater, for example, which would be, you know, draining some of the energy as well. You might be operating at really high speeds. You might be operating, you know, air conditioning very heavily if you're in hot temperatures. And so all of these things are kind of baked in to these sets of tests to add a little bit more realism, right? Because as you add these things into your tests, you are getting closer to emulating the ways that, you know, we as consumers actually drive the vehicle. And so there's more sort of quantitative information about what goes into those test cycles in this table on the right. Okay. Any questions about this? Okay. And so, you know, why is this relevant for us, right? I think, you know, there's always going to be flaws with any sort of test procedure, right? It's not like a regulatory agency could go and, you know, emulate, well, I guess they could emulate like one particular driver, right? But in general, the way that people drive is, you know, relatively heterogeneous. And so it's really about kind of providing this anchor point, right, reference number that you can use when we think about fuel efficiency. So I can think about relative fuel efficiencies as a way to compare vehicles. Okay, who has heard of Dieselgate? Anyone? A couple people? Yeah, so this was quite big in the news. I guess at this point, almost like 15 years ago, or maybe a little bit less than that, maybe like 12-ish years ago, 12, 13 years ago. Okay, so the California Air Resources Board discovered this emissions discrepancy between EU vehicles and US models of vehicles, specifically from road tests on diesel cars. Actually, our Institute of Transportation Studies at Davis was the one that actually got the Air Resources Board and Volkswagen in the same room to kind of hash this out. So little claim to fame for some of the researchers at Davis. But essentially, what was happening is, so how do we measure emissions rates from vehicles? We put them through these test cycles, right? And then there's this sort of standardized way of understanding what the emissions impact is. So you would put these vehicles on these treadmills and you would drive them, but the test cycles are all standardized, right? These are the ones that we were just talking about. WLTP or the 5-cycle tests. And so what Volkswagen and actually a couple other manufacturers did was, as soon as the vehicle started driving, the vehicle computer would detect that, oh, this isn't someone just like driving normally. This is the test. This is the WLTP test cycle. And they would then change the way that the engine was operating so that it could comply with the emissions requirements, right? And so you could like throttle down the power of the engine, and you could do all these other things in order to game the system because the car actually knows it's being tested. And so the emission controls would get activated only when the vehicle was getting tested, and that software was widely deployed to vehicles that Volkswagen was selling. And that allowed them to reduce in the test cycles the amount of emissions that were happening. But then as soon as those vehicles were sort of on the road and not driving on the test cycles, all of those emission controls would be deactivated, so that people could have like better vehicle performance. So this ended up with criminal charges, almost $3 billion in criminal fines, $1.5 billion in civil penalties, and actual jail time for some of the executives, right? Because these are not emissions regulations in the U.S. Can be penalized criminally. They're not just like civil requirements. And so this is a sort of interesting little twist to this sort of standardization on the vehicle fuel efficiency test cycles. Okay, electric vehicles undergo a slightly different test cycle. So SAE came up with a standard to do testing for electric vehicles in order to kind of fully determine their range and efficiency. And their test cycles look a little bit differently, like this. So they cycle through these UDDS and highway test cycles, and then they have this like flat 55 mile per hour testing, and they will repeat this over and over again until it can't maintain this 55 miles per hour. They fully drain the battery, and then they see how long it takes to charge full. And this is a way to determine, again, the range and efficiency, building off using some of the test cycles that already exist. Okay, so there's a little interesting caveat here. So yeah, in 2021, there's a car magazine, Car and Driver, compared performance of the Porsche Taycan 4S compared to the Tesla Model S. Okay, the tested highway range of the Porsche was 220 miles compared to 320 miles for the Model S. That matches for the Porsche pretty closely. there's about a 227 mile range that the EPA gave based off the test cycle. But compared to the Tesla, the EPA actually has measured a range of 402 miles. So there's a huge discrepancy even amongst the standard test cycle for different vehicles. And so why is that? So you can actually find that Tesla range and efficiencies consistently are a lot higher than other vehicles in their class. And part of that actually does have to do with the fact that Tesla vehicles might be a little bit more efficient. You know, their technologies are, maybe a little bit more advanced in terms of the like inverter, motor, and so on. But that doesn't explain quite all of that difference. So in fact, Tesla takes advantage of this adjustment factor that EPA offers any manufacturers of electric vehicles. So after the MCT, which is the multi-cycle test here that I was describing before, so after the MCT, the EPA will automatically adjust the range of electric vehicles down by 30%. And that's a sort of roughly calibrated number to better replicate real world conditions, because they find that after they do this test, it again overstates efficiency, so they have this automatic factor to reduce the range of the electric vehicles. But automakers are given an option to run additional drive cycles to generate an alternative adjustment factor. Not everyone does this because it's expensive, right? Actually, running these vehicles on dynamometers can be quite pricey. To run a test could cost like millions of dollars. And so the only automakers that do this are Tesla and Audi. And so they are able to show, to get around this 30% automatic reduction. Sometimes it doesn't lead to much differences, but other times that range adjustment can be as high as like 6% on sticker value. That can be 30 to 40 extra miles. And so certain automakers, I think, so at the time that I made this slide, it was Tesla and Audi. I think a couple other ones might have started to do this. But in general, right, there is going to be a difference in the ranges that you see advertised by regulatory agencies. Yeah?
I'm sorry, could you go over what MCT stands for?
Yeah, that is the multi-cycle test, this
okay.
thing. Yeah,
Okay.
right here. Yeah.
Thank you.
Yes.
So you mentioned that performance tests of EVs and ICEs are different.
Yeah.
How comparable are those results? Like, since we have different cycles, shouldn't they be the same environment?
Yeah, that's a good question. Why do we not run gas cars and electric cars on the same cycle? It is actually mainly to do with, so people don't care so much with gasoline car, the range, because you refill really quickly, but people really wanted accurate estimates of electric vehicle range. And the problem is that actually the way that that range happens over the test is kind of nonlinear. So for specifically electric vehicles, they do run the test cycle from 100% of the battery all the way down to 0%. Does that make the comparison between gas and electric vehicles not great? Yes, I would say yeah, and that is an important point. The main trade-off is that they're willing to do that so that they can get better estimates of the range. Any other questions? Okay, as I was mentioning, despite all of these standardized numbers, remember that fuel efficiency is fundamentally going to differ based on the way that we drive our vehicles. I don't know if anyone had seen this episode of Mythbusters, right? But one of the things they conclude, right, is actually your mood will affect your fuel efficiency more than almost any other thing in your vehicle, right? So, you know, if you are, if you've got road rage and you're like stomping on your pedal all the way down, right? The amount of fuel consumption and the relative efficiency of your vehicle is going to go down a lot more than if you were to drive more conservatively, right? And so when we think about real world efficiency, you know, these numbers don't translate well because there's so much variation, not only in the way that we drive, but in the conditions that we drive, right? If it's really hot, if it's really cold, if you're driving up a mountain, or if you're going on flat terrain, right? We can't possibly accommodate all of these things. And so again, all of those numbers for whatever, you know, drawbacks I'm talking about related to the test cycles, those are just meant to represent kind of a single number that you can use to compare against other cars, right? Knowing that your personal conditions for how efficient a vehicle is going to depend on a lot of other conditions in the real world that you can't really measure in a test cycle. And that is made really apparent, right? There are, you know, these, you know, car enthusiast magazines or other, you know, more consumer-facing, like information, vehicle information groups. You know, Edmunds, they sell cars as well, right? So there are these groups that do real-world testing. And you can compare some of what has been seen in those tests compared to what the EPA ratings look like. And they're almost never the same, right? And in some cases, the real world is going to be higher. Some cases, the EPA can actually be higher. And again, just reflecting differences in the ways that vehicles are driven and the conditions in which they're driven. All right? All right, so given all of this, yeah, another kind of quick discussion. Do you guys think regulators should design tests to better reflect real-world driving or to standardize comparisons? Or we think they're good where they're at? So go ahead, take a minute or two to discuss. Okay, let's reconvene. Anyone want to volunteer? How about your group over there? Yeah, so it'd be really hard to capture, real world driving. Yeah, I think that makes a lot of sense. One thing I kind of wonder about is that there is still a very consistent difference in efficiency, and so whether or not that, even if we had one standard number, that could be improved to some degree, right? Anyone else have any different thoughts? Maybe a table over there. You guys, yeah.
Another thing you mentioned is that like vehicles will like lose efficiency and lose like power after they've used for a long time.
Mm-hmm.
And so a lot of tests are like just testing like new vehicles right off of the production line. So it's not like that over after like a period of time.
I see. Okay. Yeah, that's interesting. I've never thought about that before. So the idea, right, is that if you have a new car, maybe those efficiencies look like that. But if you have a used car, after a couple years, right, you may lose some engine power. You may, your battery might degrade. Your motor might operate a little bit less efficiently. So should we be offering that as extra information to consumers? Yeah, that's an interesting thought. I would imagine your variability problem gets even worse because the way in which vehicles degrade is going to differ, not only between vehicle models, but also, on the individual cars as well. But yeah, that's, I haven't heard that one before. That is a very interesting idea to think about and would maybe empower consumers to better understand, like, if one car degrades a lot more than another, you might be wary of that. Drawbacks would be, it would be very expensive to do this because now you're thinking about like, oh, there's, on average, we have about 1,000 to 1,500 different vehicle models on the market. So every year you'd have to test those, but then you'd have to follow up and test those consecutively year on year, right? So that would be, I think, very expensive to do. Any other thoughts? Yeah.
Well, I thought like you could just have like specific tests, like this is a vehicle driving on the highway with AC, this is the driving on with heating, right?
Yeah.
Just do a full test of that, and like we live in an age where there's a lot of computers, just compile it together based on what percentage you think you're going to be driving with.
Yeah. Certainly, I think that would be an interesting thing to do. You would be asking consumers more information, right? And so the question is if they would be able to like comprehend all of the like inputs that would be needed. But yeah, certainly that would lead to more sort of accuracy.
I mean, depending on, again, that's just could be UI design.
Yeah.
Spend some time in that. Do a good UI, it doesn't feel like a chore,
Yeah, yeah. So give a better calculator to the customer to be a little bit more customizable in the way, in reporting the way they drive the car to get at their efficiencies. Yeah, the other thing that I think folks have thought about in the current day and age of vehicles where we have a lot more advanced telemetry is why not just, instead of having these tests, these standardized tests, just get all that information from new vehicles and create distributions of the efficiencies based on all of the real world use that we observe happening in cars today. And so there are some concerns with that in terms of like privacy and information sharing and that sort of thing. But I mean, you couldn't do better than actually, sampling from real world driving. And so that's one other avenue that yeah, might come to fruition in the future in terms of thinking about how we calculate efficiencies. Okay, any other comments?
Like for that, it could be like if it's a general thing where it's taking data from actual cars, you have an opt-in, right? Like if because cars are a lot of computing anyways, you could just have a very obvious opt-in every time you do maintenance. Like for this maintenance cycle, we're gonna collect the data of the efficiency and just that.
Yeah, yep. And then there's a whole question of,
Create a system to enforce that.
yeah.
So like it's not stuck in there.
Yeah. The only issue with that is that like inspections for vehicles, so thinking about using inspections as the standard way of data collection, that does happen in some places, except that vehicle inspections differ from state to state. And so in California, for example, we inspect vehicles once you've owned them for 6 years, and then you have to get them inspected annually. Electric vehicles actually don't get inspected in California. And then depending on the state, right, that can differ. And in many states, there are actually no vehicle inspections. So yeah, you have to figure out from an implementation perspective kind of the best way of doing it given those particular limitations. Okay. Other things to think about with efficiency are on-cycle versus off-cycle. Okay, and so typically when we talk about on-cycle efficiency, this is in reference to the like fuel consumption and energy consumption of actually moving the vehicle, using the drivetrain, getting from point A to point B. But you can improve efficiency by doing certain things to the vehicle that have nothing to do with the operation of the drivetrain itself, right? So for example, the lights of the vehicle, if your headlights are, halogen lamps versus LED, the amount of energy consumed is different, even though it doesn't actually affect, right, the drivetrain portion of this. And so the lights part of it wouldn't show up on like a drive cycle test. The AC and thermal management part of it isn't going to show up outside of the like air conditioning load in one particular test. The aerodynamics of the vehicle, right, can affect efficiency a lot. That's not even going to show up on any drive cycle test because that only shows up when you're moving the car through the air, right? And with a dynamometer, the rollers on the dynamometer are meant to kind of try and reflect air drag by increasing friction, but they don't differentiate between different car aerodynamic shapes. And so that's another area that we would consider to be like an off-cycle test. Okay, and so there are a number of these off-cycle things that you could do to improve fuel efficiency. This is like a small select list of some of the off-cycle efficiencies measures that can be taken in gas cars and what are the relative efficiency improvements that you might get. So something like reducing the vehicle weight, low rolling resistance tires. Low rolling resistance tires is actually one of the most cost-effective ones when automakers look to improve fuel efficiency. This is like one of the lowest hanging fruit. It's very cheap and can actually improve efficiency by quite a bit, right, up to 4%. Transmission, like CVT, continuous variable transmission, dual clutch transmissions, hybrid technologies like start-stop ignition, all of these things can improve the efficiency of the gas car and are not sort of really related to the direct drive cycle performance. And in regulation, there have been credits provided to automakers who pursue some of these technologies as a way to comply with fuel efficiencies regulations. And that is a way that you can incentivize manufacturers to essentially do these things. Because without those special credits for off-cycle technologies, they wouldn't get the benefits. Those benefits often wouldn't show up in the test cycle. Okay, what would that look like in the electric vehicles for drivetrains? So this would be on-cycle this would be things related to the on-cycle efficiency. So your battery inverter motor system are the most obvious places for improvement. A lot of companies have spent considerable resources, kind of Tesla leading the way here. Motors have already improved like 10 to 15%, which is, quite groundbreaking in such a short amount of time. Inverters are already pretty efficient, but there have been some technology improvements to increase that. But most inverters are already operating at like 95 plus efficiency. The other big one, so you may have heard of electric vehicles losing a lot of range and efficiency when they operate in cold environments, right? That's one of the common drawbacks that you hear in media. If I live in like New England in the winter, I might lose like 30 to 40% of my range. And a lot of that actually has to do with the inefficiencies of electric heat, which is the primary way that you have thermal management of the battery. So you have to heat it up so that it's not operating in such cold conditions, as well as heating your cabin, right? So making sure that you are not sitting in a car in freezing conditions and it's like, in freezing temperatures inside of your car. So you have to heat up both the cabin and the battery. And that can be extremely taxing to the battery because electric heat is very inefficient. So more recently, some vehicles are starting to put in heat pumps rather than electric heating elements. And heat pumps will drastically improve efficiency. They are actually, they're kind of more than 100% efficient because they actually derive heat out of the environment. So the heat energy that you get compared to your energy input is actually higher than that energy input. So 1 kilowatt heat pump can generate the equivalent of 2 to 3 kilowatts of heat. And that energy is actually coming out of the ambient air. So a heat pump really is essentially like an air conditioner in reverse. You're drawing energy from the sort of surrounding air. And this has been implemented in a small number of electric vehicles at this point. Like some models of the Tesla Model 3 have it. The Hyundai Ioniq 5 has it, for example. And a couple other vehicles are starting to implement these. And so these will operate much more efficiently, and you won't see quite the same reduction in range and efficiency when you're in really cold climates with EVs. So how to drive an EV efficiently? If you're interested in trying to drive an EV and make sure you're getting the most bang for your buck out of this, some of these will pertain to any vehicle, right? Conserve momentum, avoid fast acceleration and braking, operate the vehicle at the motor's highest efficiency, so 20 to 30 miles per hour. And so if you're doing a lot of city driving, you're gonna actually get a lot more range out of your vehicle than driving at highway speeds. Reducing use of heating and air conditioning. The big one, and this is for gas cars too, actually, maintaining tire pressure. Make sure to check your tire pressure regularly. That can decrease your efficiency by quite a lot, 10+%. A lot of vehicles have like eco mode, and what that actually does in your vehicle depends on specific configurations depending on the automaker. But in general, for electric vehicles, all this is doing is dampening the sensitivity of your accelerator pedal. And so when you press down on your accelerator, when you're in eco mode, it'll make you accelerate kind of less quickly. But really, it's not changing the operation of the motor itself in any fundamental way. And so if you were to stomp all the way down, it wouldn't look any different from any other aggressive sort of driving mode. It can regulate power to off-cycle things like AC. And so, yeah, eco mode is like a very generalized sort of configuration that automakers will do different things to try and improve the efficiency of your vehicle. Okay, the very last slide that I'll talk about for today before our quiz. Yeah, hypermiling. This is a fascinating like subculture amongst like fans of EVs that developed, where people do these like little, I don't know, competitions to see how far they can get on a single charge on their electric vehicle. A couple years ago, the slide that I used when I taught this 2 years ago, Tesla Model 3, there's this group of people who drove it on a closed circuit lap, and they were able to get 606 miles out of it. That record was broken by Lucid. They had 765 miles last year, and then just in the fall, it was broken again by GM. They took their Silverado. They actually were not driving on a closed circuit course. They were actually driving on real roads. They were maintaining like 20 to 25 miles per hour the whole time. No air conditioning, and your windows have to be up, otherwise you actually you increase drag. So I've heard it can be quite miserable to try and do some of these things. But yeah, they were able to get over 1,000 miles on a single charge. So yeah, some people take this pretty seriously, but in general, efficiency for electric vehicles, we've heard about how that gets measured and how we think about it in the real world. Okay, that's it for today. I'll go around and pass out quizzes. Mind the slide. Oh, just three? Okay. Yes. Yeah, sure. Yeah, you guys can just start when you get the quiz. Most states. Okay, let's put them over here and separate in ABC. You mind collecting everything? I'm gonna run off to a QE. So just put them over here in ABC.
We're missing a paper.
Oh, you are? Okay. Sorry about that. Here you go.